Okay, let's start. Today we are going to talk about the determinant. So today we will just introduce the determinant. So what is the determinant? What is the determinant? People understanding the determinant. Let's recap our previous definition of the determinant of two by two matrix, right? So if you remember the middle school or the high school math class, there was the inverse matrix, right? So, okay, let's say we have a matrix A size of the 2 by 2, right? Then how can you derive the inverse of the matrix A? Something like this term with the matrix this one, right? So you might be you might remember what does how can we derive this, but here is very interesting term, right? So AD minus BC term, right? So here actually because this is the constant term, right? So this should be non-zero to be defined in the inverse of matrix A. So in this case, this AD minus BC is called the determinant A, determinant of A. Okay, so in other words, if we analyze the determinant of A, then we can say that okay, matrix A has an inverse or not, or matrix A is invertible or not. Okay, so that's why we have to know the determinant. Okay, so by the way, we already know the how can we estimate the determinant of 2 by 2 matrix. Then the question is how can we find determinant of the larger scale matrix, something like the 3 by 3, 4 by 4, or 10,000 by 10,000, something like that. Then today we will introduce the systemical way to find out the determinant. Okay, so okay, this is the 2 by 2 matrix case. Let's think about the 3 by 3 matrix case. Okay, so let's say we have a matrix A, something like A11, A12, A13, something like A11, A12, A13, or and A21, something like A3 by 3. Okay, separate that. Then first of all, let's row reduce this matrix A to echelon form. Then see the echelon form of this matrix A. Okay, so if A11 is not equal to 0, then we can multiply this A11 to second row and third row, right? Then because we want to remove this one, right? Then by multiplying A21 to row 1, then we can replace, we can subtract from this row to this row by this one, right? Then this will be removed, then this one here, and this one by A21 should be here, right? With the minus operation, right? Then we can also estimate this one from here and here, right? What about third row? It is 0, right? Then this one, here with the A31 here, and this one, something like that. Okay. Then what do we want to do next? We have to remove this one, right? by using this term in row 2, right? So if you perform the subsequence of row reduced algorithm, then we can finally eliminate this term, and get the A1 times the what was that? How can I read this? Square? No. Okay, let's search that. Just triangle? No, it's not a triangle. There's some terminology to read this, but just let's say that this is a triangle. Okay, so triangle with the blah 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 blah. It's very complicating, but it's very today intuitive or straightforward to derive this one. Okay. Anyway, by using the row reduction algorithm, we make the echelon form of the matrix A here, something like that. Okay, and then matrix A is invertible. Then this triangle must be non-zero, right? So in other words, this if this triangle is the zero, then this row are all zero, right? Then they are not invertible. The matrix A are not invertible, right? So this triangle must be non-zero. Then in this case, we call this triangle as a determinant of a 3x3 matrix A. So this triangle has a same role of this one in 2x2 case. Okay, so this is called the determinant of the 3x3 matrix. Okay, so what does it mean? So the determinant of 2x2 case was something like this, right? And 3x3 case was something like that from here. I will not derive the every terms. So, but if you have some time, if you have some interest, please try to derive this one. Actually, it's not so difficult. So please try to derive this one. Anyway, we already know this is the determinant of 3x3 matrix. Then okay, let's reformulate this term. First of all, here from here we can make the one term. From here and here there's another term, so like that. And last one, let's use this one. Here. Okay. Interestingly, if we extract the A11 here, remaining part are determinant of this one, right? Because the determinant of A was this one, right? And if we extract A12 here, remaining things are determinant of this one, and A13, this is A13, right? If we extract A13, then remaining things are determinant of this one. Okay, so and then if we define this one as a determinant A11, then we can represent this term as A11 times determinant A11 and minus A12 times determinant A12 plus A13 determinant A13. Okay? So in other words, the determinant of the 3x3 matrix can be represented by determinant of the 2x2 matrix. Okay? So So okay, people move on. A11 define something like that. So let's say Aij denote the sum matrix formed by deleting ith row and jth column. So if the A matrix something like this, then A 3 by 2. So deleting third row and second column, then remaining thing 1 2 0 1 2 0 here 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 here. Okay, so this is the definition of the A32. Okay, so here. Okay, so the determinant of the 3 by 3 matrix can be represented by determinant of 2 by 2 sum matrix defined something like this, right? Then in other words we can now have a recursive definition of the determinant. So what does it mean? So if n is equal to 3, determinant A is defined using determinant of 2 by 2 sum matrix ai, j, or aij, like this. Or if n is equal to 4, the size of the matrix is 4 by 4, determinant A is defined using determinant of the 3 by 3 sum matrix. Okay, in general, n by n determinant is defined by determinant of the n1 minus 1 times n1 minus 1 sum matrix. Okay, so by recursively serving the determinant, we can easily find out the determinant of a larger scale matrix. Okay, so this is our main strategy. Then let's derive the systemical way. Okay, here is the systemical definition. First of all, 1 by 1 matrix A. Actually, 1 by 1 matrix is just what? Scalar, right? Or just a constant value, right? In this case, the determinant of matrix A or determinant of the scalar is just the scalar value itself. Okay, then for n is larger than 2, the determinant of the n by n matrix is the sum of n term of the form plus minus a1j determinant a1j with a plus minus sign alternating, where the entry a1, a1, 2, a1, n are from the first row of the matrix A. Okay, so actually this definition is this definition looks complicating, but if you remember this example, it's really easy to derive, okay, or understand. Okay, so from this definition, determinant of A is the a11 determinant a1 plus 1 and minus a12 times determinant a12. Why there is the negative value? We will see the why there is negative value, but here let's just remember there is the sign alternating plus minus, so blah 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 blah. Then final term is the negative 1 with the superscript 1 plus n times a1n times determinant a1n. So something this can be represented in a summation manner. something like this. Okay, so this is the general rule of the general rule to compute the determinant of the larger matrix. Okay. Okay, so here's the example. Okay, if there is a matrix A, something like A12, A1n, A21, AN1, ANN, then this first term is this one times this matrix, right? Let's use the particular. Okay. This one times this one times the determinant A11. Then what about second term? A12 times this matrix A12, something like this. Then last term is this one times this one, what was that? 1n, like that. So this can be represented something like this. Okay, so this is the definition of the determinant. Okay, so let's try to compute the determinant of the matrix A. Okay, so first of all, what I want to do is the A1 times the determinant A11. Next A12 times determinant A12, and A13 times determinant A13. Okay, so 1 times determinant this one, right? And minus 5 here with this one here, right? Plus 0 with determinant here, right? Then we already know how to compute determinant of this one, right? So 0 times 0 minus 2, right? And 0 minus 0 minus 4 minus 0, right? So finally determinant A is negative 2, right? In other words, or we can represent determinant of this one as this, something like this, because it is difficult to write the determinant in every time, so we introduce a new notation to represent the determinant, something like this, like that. Okay. So where's that? Yeah. So here's the negative sign. Okay. Anyway, so this is the systemic way to compute the determinant of the larger matrix. Using the similar way, we can estimate the determinant of the 4x4 matrix, 5x5 matrix, 6x6 matrix, something like that. So in a similar way, but it might be it might be labor intensive, or it might be tedious. It might be tedious way to derive the every step, something like this one, because there are so many operations here. So we need a more efficient way to determine or compute the determinant. Okay, so let's find out a more efficient way. Okay, so to compute determinant more efficiently, we introduce a cofactor. So what is a cofactor? The I, j cofactor of matrix A is the Sum is a number Cij. The Cij is equal to something like this. Something like this. Okay? So from concept of the cofactor, we can rewrite the determinant of the matrix A is something like this. Okay? Then this formula is called the cofactor expansion across the first row of matrix A. So from something like this, right? Right? Then from this concept, from this cofactor, we can use the not only use the first law but also use the another law to compute the determinant. Okay, why is this operations useful comparing to the only using the first law? Let's see the reason. So here's the theorem. The determinant of the n by n matrix A can be computed by the cofactor expansion across any row or any column. So in other words, determinant of matrix A can be computed something like this. So AI1 CI1 plus AI2 CI2 plus AIN CIN. So rather than just using first row, then we can use any row as a reference to compute this one. Okay? So or we can use the columns, something like this. In other words, rather than using the row as a reference, we can use the columns as a reference to define this one by using the cofactor concept, right? Okay, let's redraw here. So let's say there is a matrix A, something like A11. Then we can compute the determinant using this one, or this one, this one, this one, this one, right? This one, right? Right. This is the cofactor expansion across the ith row, or A11, N1, or we can use this one, something like that, or this one, column vector. So yeah, here, or this one, right? So rather than using the row first way, we can also compute the determinant using the columns, any columns. Okay, so it will be generalized this operation using the cofactor concept. Okay, why this one is people moving on. Let's think about the sign of the cofactor, because the sign is determined by the -1 superscript 1 plus j. So the sign plus or minus sign in I, j cofactor depend on the position I comma j, regardless of the sign of the I comma j. What does it mean? The sign of the I comma j is not important, but the location I comma j is the important the signal to determine the sign of the cofactor. So in other words, so if this is if this is the shape of the matrix A, then this one is the 1 by 1, right? I is equal to 1, j is equal to 1. This is I is equal to 2, j is equal to 1. This one is the I is equal to 1, j is equal to 2, something like this. So so the position of this ij determine the sign, something like this. So this sign of this cofactor determined by the position of the I1 or I2 or IJ or 2J. Okay, so this is the sign of cofactor. So let's think about why this one is useful. So here's the example. Let's use the cofactor expansion across the third law to compute the determinant A. Okay, let's do the similar things here, but by using the third law. Okay, let's do that. Determinant A is equal to A31 with a C31, A31, C31 plus A32, C32, then A33 and C33 here. Okay. Then the design here, this one, designs determined by position, right? Then we have to compute the this one, something like this, right? But interestingly, this one, A31, A32, no, A31 here, A33 here are 0, right? So this term will be the 0. Actually, we don't need to compute this one because they are all 0. So we only need to compute this one, right? So this is -2. Okay. So interestingly, comparing to this example, that ignoring this one only because they are 0 here. If we consider the third law, there's 2 zeros here, so we can reduce the computation complexity when computing the determinant. Okay, so that's why we generalize the previous way to compute the determinant to this theorem. Okay, in other words, we can pick the best column or best row to compute the determinant in an efficient way. Okay. Here is the extreme case. Compute the determinant A, something like this, right? So if you compute the determinant A using this theorem, using this computation, it might be very it might be very time consuming, but interestingly, if we consider this column, something like this, there are all 0, right? So in other words, this term will be 0. So we don't need to compute this one, this one, this one, and this one, right? We only need to compute A11 times A large A11 here. So determinant of large A11 here, okay? So this one and this one, right? So we can reduce the unnecessary computation for computing this one, this one, this one, this one. Okay. Then how can I compute the determinant of this one? We can also consider this one, right? Because then we can remove the unnecessary computation for this one, this one, this one, right? Okay, let's do that. So from this one, determinant of this one, we can represent determinant of A to this one, right? So what I have to do next? Interestingly, for every row and every columns, if we pick the this one, right? This one or this one, the computation would be much easier than the other choice, right? So here, let's choose this one. Okay, so 3 times 2 times where is that? Here with here, right? So 3 times 2 times 2 times this one, right? So with some sign, so it will be the positive 2, right? So anyway, this one. So finally, the determinant of the A is equal to negative 12. Okay. Okay. So here's very interesting observation. So if the matrix A is the triangular matrix, something like this, right? This is triangular matrix. Then determinant A is the product of entries on the main diagonal of the matrix A. So what does it mean? So we will skip the proof, but we can use the same strategy from the previous example to understand this theorem. So interestingly, in here, what was the determinant of this one? This one times this one, right? So from here we can see the determinant of matrix A is this one times this one times this one times this one. Okay, it's very easy, right? So in other words, without computing the very complicating computation, if we have the echelon form of the matrix A, then by multiplying the diagonal term, we can easily finding out the determinant of matrix A. So this is the determinant of the triangle matrix theorem. Okay. So this is the concept of the determinant, and today we just discussed the how can we compute the determinant. Then the next week we will talk about what is the property of the determinant and how can we use the determinant to understand the matrix A. Okay? Thank you for listening.